This is Unit 4, Chapter 15, Section 15.8, Triple Integrals in Spherical Coordinates. So another useful coordinate system in 3 dimensions is the spherical coordinate system. It simplifies the evaluation of triple integrals over regions bounded by spheres or cones. So the spherical coordinates given by rho, theta, phi, of a point P in space are shown in Figure 1, where we define rho as the magnitude of the line from the origin to point P, and rho is therefore the distance of that from point O, from the origin to P. Theta is the same angle as in cylindrical coordinates, so measured from the positive x-axis in the xy plane. And phi is the angle between the positive z-axis and the line OP. Now, given all of this, we know that rho is going to be greater than or equal to 0. And we know that phi will be between 0 and pi. The spherical coordinate system is especially useful in problems where there is symmetry about a point, and the origin can be placed at that point. So, for example, if we look in Figure 2, we have a sphere with the center at the origin and the radius of c, and we can have then the sphere defined by the equation rho is equal to c, and this is then the reason for the name spherical coordinates. The graph of the equation theta equals c is a vertical half plane as shown in Figure 3. And then the equation phi equals c would then represent a half cone with the z-axis as its main axis, as shown in Figure 4. So the relationship between rectangular and spherical coordinates can be seen from Figure 5. So if we look for triangle OPQ, we're going to see then that our z height is going to be rho cosine phi, and from triangle OP, and then we call this P prime, so O to P prime, we're going to have that R is going to be rho sine phi. So, because we know that x is equal to r cosine theta and y is equal to r sine theta, we can convert from spherical to rectangular coordinates using the following equations. We would then have that x is equal to rho sine phi cosine theta. This should be y is rho sine phi sine theta. And then z, we already have, is rho cosine phi. The distance formula gives us that rho squared is x squared plus y squared plus z squared. And we can use this equation in converting from rectangular to spherical coordinates. So let's take a look at example 1. We have the point 2 pi over 4 pi over 3 given in spherical coordinates. To plot the point and then find its rectangular coordinates. So as we see in Figure 6, we begin with the theta is pi over 4, and we move out pi over 4. From the z-axis, we come down pi over 3, and then we go out to the point 2 with the radius or rho of 2. We have the equations x is equal to rho sine phi cosine theta, y is equal to rho sine phi sine theta, and z is equal to rho cosine phi. And so we can simplify these by, we have 2 times the sine of pi over 3 times the cosine of pi over 4, which gives us then the square root of 3 over 2. For y, we have 2 times the sine of pi over 3 times the sine of pi over 4, which is also square root of 3 halves. And then we have z, which is rho cosine phi. So we have 2 cosine of pi over 3, and that gives us 1. So therefore, in rectangular coordinates, our point would be square root of 3 halves, square root of 3 halves, and 1 in rectangular coordinates. So to evaluate triple integrals with spherical coordinates, we're going to use the counterpart of the rectangular box that is considered a spherical wedge. And it's given by the equation E is equal to all points rho theta phi, where rho is between A and B, theta is between alpha and beta, and phi is between C and D. We also then have that A is going to be greater than or equal to 0, beta minus alpha must be less than or equal to 2 pi, and D minus C must be less than or equal to pi. Now, although we've defined triple integrals by dividing solids into small boxes, it can be shown that dividing a solid into small spherical wedges will always give the same result. So, if we divide E into smaller spherical wedges by means of equally spaced spheres, rho equals rho sub I, half planes, and half cones, we can arrive at equation 7, or figure 7, where we can approximate our small spherical wedge as a rectangular box with dimensions given by delta rho. We have rho sub I delta phi, which is this piece here. So rho sub I delta phi. And then lastly, we have this piece here, which is rho sub I sine phi delta theta. So we can then approximate our volume delta V as delta rho, rho sub I delta phi, rho sub I sine phi delta theta. Reordering our terms, we end up with rho sub I squared sine phi delta rho delta theta delta phi, where each of those points are some point in that spherical solid. If we then have our rectangular coordinates of these points, we can write the triple integral as f of x, y, z dv is equal to our limit as L, M, and N all go to infinity of our summation from I equals 1 to M, J equals 1 to N, and that should not be it, and K equals 1 to N, L, M, N, of our subpoints f of x, y, z, delta v, which then becomes the limit as L, M, and N all go to infinity of our summation, again, I equals 1 to L, J equals 1 to M, K equals 1 to N, of this becomes rho sine phi cosine theta, rho sine phi sine theta, rho cosine phi, converting our x, y, and z, and excuse me, I'm going to have to extend this out here, then rho squared sine phi delta rho delta theta delta phi. This sum is a Riemann sum for the function given by f of rho theta phi, which is then a function of rho sine phi cosine theta, rho sine phi sine theta, rho cosine phi, and then rho squared sine phi. And consequently, we've arrived then at the equation 3, which is the formula for triple integration in spherical coordinates, where E is the spherical wedge given as we previously defined. This formula says that we can convert a triple integral from rectangular coordinates to spherical coordinates by substituting rho sine phi cosine theta for x, rho sine phi sine theta for y, and rho cosine phi for z, using the appropriate limits of integration, and then replacing dv by rho squared sine phi d rho, d theta, and d phi, as is illustrated in figure 8. So in example 4, we are going to use spherical coordinates to find the volume of the solid that lies above the cone given by z is equal to the square root of x squared plus y squared, and below the sphere defined by x squared plus y squared plus z squared is equal to z, as shown in figure 9. So we know that the sphere is going to pass through the origin and will have center 0, 0, 1 half. And how we arrive at that, we have x squared plus y squared plus z squared minus z is equal to 0. We're going to complete the square in order to simplify this. So z squared minus z, and take the second term, divide by 2, square it, so we have 1/4 is equal to 1/4. And that gives us then x squared plus y squared plus z minus 1/2 quantity squared is equal to, and I'm going to write this as 1/2 squared. So that gives us then our center of 0, 0, 1/2. We can write the equation of the sphere in spherical coordinates as rho squared is equal to rho cosine phi, or simply rho is equal to cosine phi. The equation of the cone can then be written as rho cosine phi is equal to the square root of rho squared sine squared phi cosine squared phi plus rho squared sine squared phi sine squared theta, and I apologize, this should be a cosine squared theta, which then simplifies simply to rho sine phi. So this gives us then that we have sine phi is equal to cosine phi, which then implies that phi is going to be pi over 4. And therefore, the description of the solid E in spherical coordinates is then given by rho theta phi, where theta is between 0 and 2 pi, phi is between 0 and pi over 4, and rho is going to be between 0 and cosine phi. Now we can see in figure 11 how E is swept out if we integrate first with respect to rho, and then phi, and then theta. And so then we have the equation. So then we have the equation that the volume of E is going to be given by the triple integral over E of dV, which is then going to be given from 0 to 2 pi, 0 to pi over 4, 0 to cosine phi of rho squared sine phi d rho, d phi, and d theta. And I would have you complete this portion of the problem for the video.